then we join two vertices if two representatives of the corresponding classes were joined.
I see now what you're doing, because for rank 2 you get just this 5 vertices, right?
Yeah, and we obtain a pentagon.
Yeah, that is going back to what Marta was doing, right?
Exactly.
Ah, I see.
Exactly.
And like one of these children, it has to be explained why one has to do something, otherwise I don't feel content in doing it.
Yeah, I will do the example of it as mine.
I know, but I have to be motivated.
So of course in the four finite cases in rank 2 we obtain a square in type A1 times A1 and the pentagon.
So when rank is higher, you get like a three-dimensional, you get multi-dimensional thing, right?
Yes.
You get this strange object.
I mean, they're always a graph. They're always graphs.
No, it's graph, but if you want to look at it geometrically, it will be embedded into some space of higher dimension, right?
Yeah, so there is there are some papers on the polytopes that you may obtain in a three-dimensional case at least, or maybe also higher dimensions. The so-called association examples of this solution.
Association.
Yes, because these are. So the vertices were. The vertices correspond to all the possible way to multiply n elements if the associative property doesn't apply. So all the possible brackets you can put in.
No,
or something like this, and then the edges were just simple movements in these brackets.
No, I know.
But do I remember? But
This
this
is
is an example of cluster algebras, of exchange graphs of cluster algebras in higher dimension. Well, I saw a talk once, so I don't know.
You remember the talks you went to? I'm very impressed. Because the moment I walk out of the door, it's gone.
Yes, then what are the other cases? We had maybe the epsilon. No epsilon. So in type B2.
The example has to be more detailed for me.
Huh?
The example has to be more detailed for me. You cannot just.
Oh, this is just the period. So in types A1 times A1, remember H is 2, and so the period is 4, and so you obtain a square.
No, but we studied in detail A2 case, right?
Yes, in type A2, we saw that we had the period. It's 5, so.
See.
So any 5
No,
vectors you.
No, but I want to see the Marta approach, right? That she was putting the clusters, right? You remember? No.
Yeah, I can describe it
later.
No,
okay.
Also now.
No, I can wait. But just don't write these little pictures with no explanation because I'm not helped with by this.
Okay. No, I will do this description. Type A2. Okay. Type A2. So these were the variables of the vertex T1. Then in T2, we have y3 and y2.
Hai fatto te che scorderai tutto.
And then y4 and y3, this is t3. And t4 we have y4 and y5. And t5 we have y5, y6. And finally t6 we have y6 is y1. No, yes, y6 is y1. And so t6 is y1. So I write it in the first row here, the variables which have index 1, and in the second row the variables which have index 2. So this y2 is x1 of
Will you
t6.
help us with the concept of index? We forgot. I forgot.
This index. This
Guarda. Non ci siamo proprio.
the cluster variables of a vertex t were denoted by x1t, x2t, xnt.
Sì, sì, ma guarda, così non capisco niente proprio, niente, nothing, I'm out of it. I don't understand the correspondence between the y's and the x's. You have to be
They're the
clear.
same.
I understand, but they're not the same
For
as you
Tm,
please.
no, yeah, for
There is
Tm,
an association because you write y2 equal to, so there is some association.
yes.
You have
So-
to recall it for me.
Yes, this is the definition of Tm I have to be careful here. So if m is odd, x1 of Tm is ym. If m is even, x2 Tm is ym. So this is correct.
So the vertex Tm, xm,
And then x m plus 1 of Tm is
carta
ym plus
l'm con la bracket così, su m
Vuol dire uno o due?
1 o 2,
Uno,
seconda
sì.
So the two variables
Mm.
associated to Tm were ym and ym plus 1.
Mm.
The one with index 1 is the one which has an odd index here.
So,
And the one with index 2 is the one with an even index. So here, this y2 was actually y7.
okay.
So this is the variables with index 1 in this case. But then we proved that this is equal to y2. But originally it was x1 of t6. So in this case, the permutation sigma is actually the transposition 1, 2.
Sì.
Because the two variables are exchanged in this.
Wait. So sigma is an Sn, right? Is the only possibility because
It might be the identity. In all the other cases, it's the identity. In all the other finite cases, it's the identity.
So for B2 is the
Yeah, because this is the only case where the period is odd. In other cases, in type in B2, we have h plus 2. This is 6. Type G2, h plus 2.
So why is the rank of the, I mean the length of the permutation, why does it have to be the same as as the H.
Because we proved that y1 is equal to yh plus 3. So this index is odd if h is even and changes parity if h is odd. It's just this, nothing deep.
The fact that sigma is not the identity has something to do with the linking diagram, with the automorphisms of the linking diagram. Perhaps it just stays anyway, because B2, so
In type A1 times A1, we also have an Euclidean automorphism. So,
no.
don't know, might be. But for the other cases, it's true, yes. In the other cases, it's true, yes.
But they don't say anything of this kind.
No, for the
So
moment, they don't
it's
say
not,
anything. They just
so they
say,
go through. Just
they just give a name
chance.
to this sigma, they call it the mononymy of the extreme graph. Well, we can now take a look at the pentagon explicitly and find again what matter. So when we draw the exchange graphs, we forget the labels of the edges. Because the same edge might be labeled with 1 or 2 in the original graph. So there are no more the labels. So we are
So
probably...
this was corresponding to G2N, right? That was the...
Yes,
Okay.
it was the case of the Grassmannian of planes AN. So I will rewrite the cluster variables on the vertices. Maybe there is y1, y2 is
right.
y1, y2, y2, y3, y3, y4. Here we have y4, y5, and finally y1, y5. And we can write the exchange relations on the edges. For example, here we have y2, y4. Maybe I want to start from this. y1, y3. Remember, this was q2, y2 plus R2. But then we saw that the R2 was Q4 times Q5. Okay, so we have this exchange relation for y1.
Why do we want to eliminate the R2? Why it is important?
Because we can express all the exchange relations just in terms of the q's.
Why is it important?
It is important because these elements will be the variables on the ring of functions on the Grassmannians which were associated to which had consecutive indices. So we will see. For the moment, we just do these substitutions. We can eliminate all the coefficients r. This is just formal for the moment. And similar to this, we can find all the other relations for the r's. And for example, y2 by 4, which is q3 by 3 plus r3 becomes q5 q1. And here we have y3, y5, y4 plus, and the others. And then we see that this is actually what happens in the Grassmann. For the moment, we have just done formal computations, just supposing that we are in type A2 with and in the normalized case. So in the case of the Grassmann, we had these variables x12, x23, x34 that we considered as coefficients, as scalars, and they correspond to the coefficients q1, q2, q3, q5.
So the claim is that this will repeat.
This is just a rename of what Marta made. You just write x I plus 1 instead of qi, and now I should be careful. This is I don't know how to rename all the others, but in any case, the y's will correspond to the xij, where j minus I is not 1 or minus 1.
No, but the claim is that these relations will repeat.
Yes, these are the Plucker relations.
Yes,
These are
it
exactly.
will repeat after 5. After 5 of them,
Yes, we have proved this.
It's like,
We have proved this before, that the relations are periodic.
the Plucker.
Yes, the
No,
Plucker,
what? Bear with me. What? Of course, we prove now
that the relations are
are
periodic.
periodic. We know from
Yes.
all the cluster business.
Yes.
But with Marta, I forget. Did we prove that Plucker are actually periodic?
Yeah, but in this case, the definition of the Plucker variables is periodic. So, but in that case, by definition, x67 is x12. This was the definition of x67.
I'm confused. Go explain. I'm confused. I'm really confused.
Yeah, so in the case of the Grassmannian, we started with all variables x, I, j,
Right. Okay.
where both
Right. Sure.
I and j.
Yes.
So this is GR25.
And right. 5.
Yes. Because in the other case we have higher dimensions.
No. Okay. So it is not GR2N.
No, the
GR25.
Just
Really?
yes.
You did the GR25?
No. She studied
But dependent
the
on
general
the
case, but
5.
then we focus on this case. Yes.
No, okay. Then if it stops at 5, I understand. I mean, it will stop
But
at 5.
the other case have a higher dimension. They are always cluster algebras, but of higher dimension.
Not over rank 2.
Yes.
Not over rank 2.
Not over rank 2.
Even if GR2N will not be over rank 2.
No.
So the
And
class
actually, they will be of finite type. They are not finite. They are not of finite type.
They will not
The
be
exchange
finite.
graph will not be finite in general for the Grassmann.
No, okay. Even of rank 2, that is the thing.
And
Everything-
I told you some strange things. Maybe the case G26 correspond to D something, and then
Right,
G27 to E something, and then they are not finite.
they're not finite. That's strange.
So there's a strange pattern. It's not clear.
No, okay. This is the strange thing.
In this case, we have these variables, and then to express the Kluge relations in a compact way, we define the
No,
these variables also
okay.
for higher
There is clear
indices,
repeat of you, obviously.
modulo 5.
I thought it was GR12, no, it's GR25. Okay.
Yes. Now there is an important here. No, so maybe I can write explicitly one statement which can be generalizing in higher rank. So the following are equivalent.
This is the proposition.
This is just an observation of what we have done. Following are equivalent in the normalized case. Normalized case. Well, there are finitely many cluster variables. Two, the exchange graph is finite. Of course, these two are trivially equivalent. And three, the generalized Cartan matrix A T is the generalized Cartan matrix is associated to a final dimensional. How can I say this compactly? It's a Cartan matrix of finite type. I guess in the general case, we will need the normalized and skew symmetrizable case, which is automatic in rank 2. In rank 2, all the matrices are skew symmetrizable. In general, they are not, but if it's not skew symmetrizable, you cannot define the matrix A. So this is probably the result in general for all types, for all our ranks. Then there is an important theorem which tells us that the rank 2 case is actually very important and also in the general case. This is the theorem. I just state it and then I don't know if I can proceed with the proof because it's a bit long. So suppose for two indices I and j, we have E, I, J, E, B, J, I, P, is at most 3. So that looking at this position, we are like in the finite case in rank 2. Which are the two elementary mixing. And this for some T. Okay. So let H be the corresponding And then, starting from T, we proceed with a path which labels alternating I and J. Getting to T prime, path of length H plus 2. So in the case of rank 2, we know that T and T prime are equivalent. This theorem says that this is always true. And T and T prime are equivalent. And the conjecture here is that the equivalence among all vertices is generated by equivalence of this form. So
It's
if
not proved. They don't prove it.
they don't prove it, they just conjecture this. And I don't know if this is true. So this is what happened for a Coxeter group. If you take two reduced expressions of two elements, you know that you can go from one to the other and just looking at subwords which alternates I and J and J, SI and J.
Can you repeat this for?
So this conjecture has a classical counterpart in Coxeter group. If you take two reduced expression of
Yes.
an element, as you can go from one to the other, just doing elementary position of subwords which are words which alternates SI, SJ, SI, SJ. So
Can
this
you repeat how you go
element,
from one to the other doing what? You go from one to the other doing, I didn't hear.
Yes,
because
yes,
of
I
the
couldn't
traffic. It's not that I didn't understand, I didn't hear.
so if you have a subword here of W,
Uh-huh.
say in type A2, okay, for example, in type A2, no, because I don't find the right words. So in type A2, if you have a subwords of the form SI plus 1 SI, then you can replace this by SI plus 1 SI and SI plus 1.
Yes.
And we know that we can pass from a reduced expression to another just doing this
Of this
elementary operation.
alternating, this substitution of this alternating.
Exactly.
Of arbitrary length, no.
Of arbitrary.
Of arbitrary.
Yeah, the length must be the longest possible for the two indices.
No, okay. No, but you don't just do it for the longest. You do.
What do you mean the longest?
I mean, there is a
It should be
longest.
the longest
They
word
have reduced.
the longest reduced word in the two letters.
I'm saying not with a fixed length. You could be doing it with. No, because
If you
then.
have two letters ST,
No, yes, but it says let H.
in this case the length is necessarily H plus 2.
Right, here too, you fix
Here the length should be necessarily H.
necessarily H. So you fix the length. It's not that you use some length in one instance, different length in other instance. No, that length.
Of course, for example, in SN,
Yes, yes.
if you want to replace
Yes.
S1, S2, S1,
You replace with
you
that.
replace
No,
this
it's
with
clear.
S2, S1, S2.
Because
And
this is
the only length where you can do this
the
operation.
longest element.
Yes, this is the
Okay,
longest
this is
element.
what this
The
is.
longest
what-
reduced element in these two letters.
I understand. And so this.
So this is the fifth word theorem. This
No,
is
no,
called
I know.
this way.
is,
And this conjecture is somehow the
it's a generalization.
generalization of this.
This is, I mean, it seems they're very strictly related because, no?
It should be, but if it is still a conjecture, I mean,
No,
it is
no.
it is It's
No, I
much
have
bigger.
I have a
Of course,
very, no, I have a very elementary question. We say rank 2, we already seen this, okay?
Yes.
Yes, but but we.
But for rank 2 is
no, so
it's
the
failure.
theorem.
The statement is empty for.
So the constructor states that T and two vertices T and T prime are equivalent if and only if they are joined by.
No, if and only if there is a sequence T T1 equivalent to T2 equivalent to T prime, such that any pair of consecutive vertices here is in this situation. So that yes.
No, I
The
see.
equivalence relation in general is generated by this.
No, because all the theorem we've seen up to now was for rank 2. All this theorem about the delta and stuff like this was for rank 2, right?
Delta?
No,
Yes.
Ah,
For full
because
systems,
it's
yes.
not for general.
No. But this theorem will have a general counterpart. This
No,
is
no,
true
this
for
is-
all types.
No, but this
But
is
this-
clear. This is clear why, because it's very general, but
Yeah,
what
this is a paper
is-
on inventions of 50 pages, but then it's clear.
no, you understand what I mean. I mean,
Yes.
it's,
I mean, this also will be clear.
no, because the procedure we have seen for the delta is the procedure that strictly depends on the fact that we're in rank 2. So it's not that it's so easily generalizable. This
Yes.
is what I had in mind. So I was thinking, oh, this is really clear. But no, it's not clear because that procedure, we saw it especially designed for the case 2.
Yes.
In case it's more than just 2, the cluster variables, will be more. And here the fact that 2 plays a key role because there is just this line going from one to the other. It's not.
Yes.
Before trying to prove something, you have to understand it is believable. So that is very
Yes.
believable. This is less clear now.
Why do you need the condition, that condition on the bound on the BIJs?
The condition, sorry?
You need the condition on the BIJs, right, and the BJIs.
Yeah.
So why do you need it?
This is the condition that we had for in the rank 2 for being in the finite case.
Okay.
So
that
remember
implies it.
we had in that case B, C, that would be at most 3.
Okay.
So in this case B is BIJT and C is
Oh,
BJIT.
I see. Okay.
So that we are the only possible case where 0, 0.
Yes.
Since they must have opposite sign,
Mhm.
and then
Okay. So we had our finite list of the corresponding to the
Yes. yes. There are just 4.
Right.
Four
Right.
cases.
Do they have more evidence for the conduction?
Non
Just
è
a-
niente,
And,
C'è una
maybe-
che saprà.
yes, we can ask him some questions about it. His conjecture. I think I'm not going to show you the proof today because it's a bit long. Maybe in the next lecture we'll finish the first paper doing this proof and then a very nice example.
Dopo basta cluster, ancora cluster. Facciamo
Dopo
cose più
basta.
divertenti.
Sì.
Facciamo Alice Chandra Modules.
Vabbè.
No, scherzato.
No, per me basta.